This is a response video to The Lever Paradox by Steve Mould. So if you haven't seen that, go watch it now, or else this won't make any sense. In The Lever Paradox, Steve described an apparent paradox that appears when you use a lever, or pulleys, or slopes. Anyway, the paradox was that the relationship between the force he was putting onto the lever with his hand and his hand's resulting acceleration didn't seem to follow his intuition. And so he asked,
then I was thinking, is there a neat way, is there something I can point to and say, look, this is where it deviates from intuition?
Yep, there is. And that's what I'll be doing here. And it doesn't depend on any dynamic systems, spinning objects, or anything fancy at all. First, I have to state this as clearly as I can because it's relevant for the rest of the discussion. But F equals ma is a definite relationship between three things: the mass of a thing, the force acting on that thing, and the acceleration that thing will experience as a result. Let's make sure we keep that in mind. So if we hold something on our hand and we apply a net force, then the way that that net force affects the acceleration of that something is described by the F equals ma relationship. Now, to make the next part more obvious, let's split this up a little more. Our hand pushes on the thing with force Fh, and our hand will accelerate at Ah. The thing feels force Fw from the hand, and then the thing accelerates at Aw. Now, just by how we set this up, we know that the forces will be equal. Fw is equal to Fh. And since we make sure that our hand keeps contact with the thing the whole time, the accelerations will be equal, that is, Aw equals Ah. And because those are equal, we can just write down a simple relationship between the force our hand is applying and the accelerations of both our hand and the weight. But remember that we're talking about applying a force to that thing, so the only reason that this relationship holds is because both the forces and accelerations for our hand and the thing are equal. When we introduce a lever, we break those equalities. The force applied to the weight is still related to its acceleration through F equals ma, but now the force experienced by the weight is no longer necessarily the same as the force that we put in with our hand. And similarly, the acceleration of our hand is no longer the same as the acceleration of the weight. And it's not just because they point in different directions now, the magnitudes of these quantities are no longer the same. And this is where reality deviates from Steve's intuition. Steve's intuition seems to be telling him that at least some of these equalities still hold. Now, it might be useful to know the correct relationships instead, so here they are. There's a link in the description with their derivation. But for now, just trust me on them. So now that we have these exact formulas, we can go through Steve's example and see which parts of his argument make sense and which parts don't.
But when I press down on a lever with a certain force, right, to keep it stationary, and then I double that force.
In other words, we're choosing the force that a hand puts in, Fh, such that the net force on the weight, Fw, is equal to the force that would be applied to the weight by gravity, Fg. And, we know F equals ma, when applied to the weight, so that means that the acceleration of the weight is little g.
My brain is expecting my hand to accelerate downwards at little g, but it might not, right? It depends what's going on the other side of the lever.
And here is a crucial mistake. All of that logic that you just went through, that holds for the mass, the weight, not his hand. F equals ma applies to the weight, and the weight is what is affected by gravity. So the weight is the thing that's going to move at little g. And because of levers, if the weight is moving at little g, then the acceleration of his hand will clearly depend on the lengths of the lever. In particular, the acceleration of his hand is multiplied by that ratio of lever lengths. I think the central thing that Steve does wrong here, the thing which underlies all of the errors that he makes along the way in his video, is implicitly assuming that F equals ma is a relationship which applies equally to any pair of force and acceleration. But if the force isn't something that's directly acting on an object, F equals ma isn't the correct relationship. His intuition is just telling him, hey, you have a force here and you have an acceleration there at the same point. Then whatever intuitions we have about force and gravity are going to apply here exactly the same way as it does to another part of the system. Because, F equals ma is always true, right? Well, no, it's not. If the force is not acting on an object, then F equals ma doesn't apply. And as we can see here, it's obviously not true when we're using levers. The exact relationship between a force and the acceleration depends on precisely which pair of force and acceleration we are looking at. So, I think the key lesson here is to remember to only apply intuitions about F equals ma and gravity to the object which we are doing work on. And then we can use that to work out the rest of the forces and accelerations on the other parts of the system. If we do that, we probably won't accidentally conclude that 1 joule equals 2 joules, and neither will we intuitively expect our hand to move at the same acceleration as an object on the other side of a lever.